The universe is hiding its greatest secrets in plain sight. Carl Sagan once said that somewhere, something incredible is waiting to be known. We are about to journey through 25 cosmic puzzles that challenge the very laws of physics as we know them. By the end of this exploration, you will understand the fundamental forces that could one day rewrite our reality. We will investigate why the cosmos is flying apart at ever-increasing speeds and what happens to information inside a black hole. What cosmic truth are you most curious to uncover? This invisible engine was first glimpsed through the faint light of dying stars. In the late 1990s, two independent teams of astronomers were studying distant stellar explosions known as Type 1, a supernova. They expected to see these cosmic beacons slowing down, their light stretched and dimmed by a universe gradually applying the brakes of gravity. Instead, they found the opposite. The supernova were much dimmer than they should have been, meaning the universe was not just expanding, but its expansion was speeding up. This stunning discovery, which earned the Nobel Prize in Physics in 2011, revealed a cosmos being ripped apart by a force we cannot see. Astrophysicist Priyamvada Natarajan calls dark energy the most profound mystery in all of science. What could this force be? The leading idea is Einstein's cosmological constant, a kind of energy inherent to the fabric of empty space itself. Think of the vacuum not as true nothingness, but as a seething foam of virtual particles that pop in and out of existence, each pair lending a tiny push to the cosmos. Another possibility is a dynamic field called quintessence, a fluid that permeates space and whose strength can change over time. Observations from the cosmic microwave background and the large-scale distribution of galaxies all confirm that dark energy makes up about 68% of the universe's total energy budget. It is the dominant player in the cosmic story, yet we have no idea what it is. Is it a property of space itself, or is it evidence of a fifth fundamental force, one that only reveals itself on the grandest of scales? This single puzzle forces us to question the very foundations of general relativity and quantum mechanics, hinting that a deeper theory of reality is waiting to be found. And as we grapple with the force that pushes the cosmos apart, we must also confront the shadowy substance that holds it together. While dark energy pushes the cosmos apart, another, more tangible mystery holds it together. In the 1970s, astronomer Vera Rubin was meticulously tracking the speeds of stars within spiral galaxies. According to the laws of gravity, stars on the outer edges of these vast cosmic pinwheels should be moving much slower than those near the bright center, just as Pluto orbits our Sun more sluggishly than Mercury. Yet her observations revealed something startling. The stars far from the galactic core were whipping around at nearly the same high speed as their inner neighbors. This could only mean one thing. The galaxies were embedded within enormous, invisible halos of mass, halos exerting a powerful gravitational pull, halos of something we could not see. This was the first robust evidence for what we now call dark matter. As physicist Lisa Randall explains, dark matter is there because we see the effects of its gravity. This mysterious substance makes up about 27% of the universe, nearly 6 times the amount of all the ordinary matter that makes up stars, planets, and us. It does not emit, absorb, or reflect any light, making it completely transparent and detectable only through its gravitational grip on everything we can see. So what is it made of? The leading candidates are exotic particles born from the hot, dense early universe. One prominent idea points to WIMP, or weakly interacting massive particles. These are hypothetical heavy particles that barely interact with normal matter, streaming through you and everything around you by the billions every second without a trace. Another candidate is the action, an incredibly lightweight particle that could be produced in vast numbers. Or perhaps dark matter involves sterile neutrinos, a heavier, more aloof cousin to the familiar neutrinos we already know. The hunt to catch one of these ghostly particles is underway in laboratories buried deep underground, where scientists hope to shield their ultrasensitive detectors from the constant rain of cosmic radiation. They wait for the telltale, minuscule vibration that might signal a dark matter particle has finally bumped into an atomic nucleus. Meanwhile, astronomers use the universe itself as a laboratory. They map the invisible scaffolding of dark matter by watching how its gravity bends the light from distant galaxies, a phenomenon called gravitational lensing. One of the most compelling pieces of evidence comes from a violent cosmic collision known as the bullet cluster. When two galaxy clusters smashed into each other, their hot, visible gas clouds, rich with normal matter, slammed together and slowed down. But the dark matter, inferred from its gravitational lensing effect, sailed right through the collision, completely separated from the gas. This proved dark matter is not just modified gravity, it is a real, physical substance that does not interact with itself or anything else in the way normal matter does. This leaves us with a profound question. Is the cosmos filled with a sea of unknown particles, a hidden architecture we have yet to touch? Or do the strange motions of galaxies and stars mean that our understanding of gravity itself is incomplete, that the rules set down by Newton and Einstein break down on the vastest scales? The identity of dark matter is not just a missing piece of the cosmic inventory. It is a direct challenge to our knowledge of the fundamental ingredients of reality. And as we search for what binds the galaxies, we must also confront the most destructive forces in the universe, the cosmic vacuums that erase information from existence. Two cosmic clocks are ticking out of sync. One, built from the faint afterglow of the Big Bang, measures the universe's expansion at a certain steady rhythm. The other, constructed from brilliant stellar explosions in our modern cosmos, ticks noticeably faster. This growing mismatch is known as the Hubble Tension, and it has become a full-blown crisis in our understanding of the cosmos. The numbers tell a frustrating story. When we look at the pristine snapshot of the infant universe, the cosmic microwave background observed by the Planck satellite, it points to an expansion rate of about 67 kilometers per second per megaparsec. This measurement relies on the standard model of cosmology, working backwards from the early universe to predict its current state. Yet, when astronomers like Nobel laureate Adam Rees and his SH0ES team use cosmic lighthouses like Cepheid variable stars and Type 1a supernova to measure the expansion directly in today's universe, they get a different answer closer to 73. The gap is small but stubborn, and as Rees states, this discrepancy is not going away, it is becoming more significant. The difference is far larger than what can be explained by simple measurement errors. This forces a difficult question. Are we missing something subtle in our measurements, some tiny, unaccounted for bias in how we gauge cosmic distances? Or is the universe trying to tell us that our cherished standard model is incomplete? The resolution might require new physics. Perhaps a form of early dark energy briefly surged in the universe's first moments, altering its initial conditions and throwing off the predictions from the cosmic microwave background. Maybe neutrinos, the ghostly particles that stream through everything, have strange properties that change the cosmic evolutionary track. The meticulous work of the SH0ES team, cross-calibrating different distance markers with incredible precision only deepens the mystery by confirming the gap is real. So what does this tension reveal? Is it a crack in the foundation of our most successful cosmological theory? A hint that we need to add a new, undiscovered ingredient to the cosmic recipe? This puzzle exposes the fragility of our measurements and reminds us that every confident number we assign to the cosmos carries with it the weight of our assumptions. Our existence is a cosmic accident, a one-in-a-billion fluke that defies the very laws of creation. In the first moments of the Big Bang, energy should have condensed into perfectly equal amounts of matter and antimatter. For every particle of matter born, a mirror image particle of antimatter should have been created. When these two meet, they annihilate each other in a flash of pure energy. If the universe had played fair, all of it should have vanished, leaving behind a lifeless, expanding sea of light. Yet here we are, in a universe filled with galaxies, stars, and planets, all made of matter. A tiny, almost imperceptible imbalance saved everything. One extra particle of matter survived for every billion annihilations. That one-in-a-billion surplus is the reason you and everything you see exists at all. Physicist Helen Quinn calls this the asymmetry between matter and antimatter, one of the most fundamental questions in all of particle physics. How did this bias come to be? The process that created this excess is known as baryogenesis, and it requires three very specific conditions, first outlined by physicist Andrei Sakharov. First, the laws of physics must somehow treat matter and antimatter differently, a phenomenon called CP violation. It means that certain processes should run slightly faster for matter than for their antimatter mirror images. Second, there must be a process that changes the total number of matter particles, violating what is known as baryon number. And third, all of this had to happen while the hot, dense early universe was wildly out of thermal equilibrium, ensuring the slight bias was not immediately erased. We have found small amounts of CP violation in the world of quarks, studied in meticulous detail at facilities like CERN, but the effect is far too weak to account for the vast cosmic structure we see today. So where did the decisive imbalance occur? The search now points to the ghostly neutrino. Experiments are hunting for CP violation in how neutrinos oscillate or change their identities. Some theories suggest a mechanism called leptogenesis, where ultra-heavy neutrinos that existed only in the instant after the Big Bang decayed, ultimately generating the matter excess we live on today. The evidence for this primordial tipping of the scales is written across the cosmos. The cosmic microwave background and the vast web of galaxies we observe could only have formed in a matter-dominated universe. The profound question remains, what unknown process in the first fractions of a second of time decided in our favor? Our entire reality hinges on a delicate, unexplained imbalance, a single vote cast for existence in a universe that was designed for total annihilation. This mystery forces us to look even deeper to the very first instant of time, where the laws of physics as we know them may have broken down completely. The very fabric of our reality was stretched beyond comprehension in its first moments. Think of cosmic inflation as a cosmic magnifying glass, one that took the tiniest quantum jitters, fluctuations that were smaller than a single atom, and stretched them across the entire sky. These microscopic ripples became the gravitational seeds for everything we see today, the future homes of galaxies, stars, and planets. This theory of a brief, explosive expansion was proposed to solve two profound puzzles about our universe. The first is the horizon problem. Look in any direction and the cosmic microwave background is almost perfectly uniform, a nearly identical temperature everywhere. But in a universe expanding at a steady pace, These distant regions should never have been in contact to equalize their temperature. It is like walking into a room and finding two people on opposite sides wearing the exact same outfit without ever having met. Inflation solves this by suggesting that all of space was once crammed into a tiny, connected volume that was then stretched to cosmic proportions in an instant. The second puzzle is the flatness problem. Measurements show the geometry of our universe is incredibly flat, like a perfectly smooth sheet of paper. For it to remain so flat after billions of years of expansion, its initial conditions had to be fine-tuned to an unimaginable precision. Inflation naturally flattens the cosmos, just as blowing up a balloon makes its surface appear smoother and flatter. Cosmologist Alan Guth described inflation as a mechanism that can explain the large-scale uniformity of the universe. The engine for this incredible growth is thought to be a scalar field called the inflaton, a strange energy field that permeated the newborn cosmos and caused it to expand at a speed far greater than light itself. The evidence for this event is written in the oldest light we can see. The subtle temperature variations and the specific patterns of polarization in the cosmic microwave background, meticulously mapped by satellites like Planck, match the predictions of inflation beautifully. They show us the imprint of those stretched quantum seeds, yet for all its success, inflation is a framework, not a single proven theory. Competing models abound. Chaotic inflation suggests our universe is just one bubble in a vast, eternally inflating multiverse, where new bubbles are constantly budding off. Other ideas, like bouncing cosmologies, propose that the Big Bang was not a true beginning, but a rebound from a previous cosmic contraction. The great missing piece of evidence is the direct detection of primordial gravitational waves, the ripples in space-time that should have been generated by inflation's violent stretching. These waves would leave a distinct curl-like pattern called B-mode polarization in the cosmic microwave background. Experiments are scouring the sky for this signal, but so far it has eluded us. The Planck data has narrowed down the possibilities, constraining the energy scale of inflation, but it has not pinpointed a single winning model, so we are left with a profound conundrum. Did inflation truly happen? If it did, what was the true nature of the inflaton field? Was it a fundamental particle, a property of space itself, or something else entirely? This puzzle forces us to confront the very first fraction of a second, a realm where our known physics breaks down, urging us to find the clues that could tell us how everything began. The final chapter of our cosmic story remains unwritten, its ending dictated by the same dark energy that now accelerates the expansion of all we see. The ultimate fate of the universe hinges on a single number, a value physicists call the equation of state parameter, or simply W. This number describes the pressure that dark energy exerts. If dark energy remains constant, a cosmological constant as Einstein imagined, then W equals exactly -1. In this scenario, the fate of the cosmos is a slow, cold demise known as the Big Freeze or heat death. Galaxies will continue to recede from one another, their starlight fading over trillions of years. Eventually, the last stars will flicker out, and the universe will become a vast, dark, and near-empty void, a uniform sea of diluted particles at a temperature barely above absolute zero. It is a quiet, almost peaceful end, but what if dark energy is not constant? What if this repulsive force grows stronger over time? If the parameter W is less than -1, we face a far more violent destiny, the Big Rip. In this scenario, the accelerating expansion becomes so ferocious that it overwhelms every force that holds things together. First, galaxy clusters would be torn apart. Then, individual galaxies. As the end nears, stars would be ripped from their solar systems. In the final, catastrophic moments, planets, molecules, and even atoms themselves would be shredded by the accelerating fabric of space. The entire universe would be torn into a spray of fundamental particles, unable to ever interact again. Physicist Brian Greene reminds us that the ultimate fate of the universe hinges on the properties of dark energy, a substance we are only beginning to probe. Current observations from supernova to the cosmic microwave background suggest that W is very close to -1, favoring the Big Freeze. Yet the measurements are not yet precise enough to rule out a future Big Rip. There are even more speculative possibilities. Could dark energy eventually decay or reverse its nature, leading to a big crunch where the universe stops expanding and collapses back upon itself in a fiery reversal of the Big Bang? Or could a quantum event, a vacuum decay in a distant part of the cosmos, trigger a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics and annihilating our reality in an instant? Simulations of the Big Freeze present a haunting vision, showing galaxy clusters becoming isolated islands, their lights going out one by one until each is marooned in an impossible darkness, forever alone. This forces us to ask a deeply human question. What does an end, whether frozen or torn, mean for our understanding of time and existence? If all structure and complexity ultimately fade into nothingness, was the grand cosmic story just a temporary flicker in an eternal silence? The answer lies in the mysterious nature of dark energy itself, a puzzle that connects directly to the fundamental constants that shape our reality, constants whose values seem improbably fine-tuned for life and for a future we cannot yet see. These invisible threads weave through the vast voids between galaxies, a silent, pervasive force shaping the cosmos in ways we are only beginning to understand. From the delicate spiral arms of our own Milky Way to the immense clusters of galaxies, magnetic fields are everywhere, influencing how stars are born and how cosmic rays, the universe's most energetic particles, travel across unimaginable distances. Yet their origin story is one of astronomy's greatest unsolved puzzles. How did these fields, often measured in millionths of a Gauss, grow from virtually nothing to the strengths we observe today? As astrophysicist Ethan Siegel notes, cosmic magnetic fields are ubiquitous, but their genesis is shrouded in mystery. Standard cosmological models face a fundamental challenge. They can describe how a weak seed field might be amplified, but they struggle to explain how that first, crucial seed was planted in the primordial universe. One compelling idea is the battery effect. Imagine a vast cloud of spinning, ionized gas in the early universe. As this charged plasma rotates, it can generate tiny electrical currents, much like a simple chemical battery, creating the faintest magnetic fields. These weak seeds could then be stretched, twisted, and supercharged by the turbulent motions within galaxies, amplified over billions of years by a dynamo effect. Another possibility is that the seeds are primordial, born in the extreme violence of the Big Bang or the inflationary epoch that followed. In those first moments, quantum fluctuations could have imprinted magnetic fields directly onto the fabric of spacetime, weaving them into the cosmos from the very beginning. A third set of theories looks to more local astrophysical engines. Supernova explosions, with their immense shockwaves, can compress and tangle any existing fields, while the furious jets erupting from active galactic nuclei can inject magnetic energy into intergalactic space on a colossal scale. To trace these cosmic fingerprints, astronomers use radio telescopes to observe two key phenomena. They study synchrotron emission, the faint glow given off by electrons spiraling at near light speed along magnetic field lines. They also measure Faraday rotation, where the magnetic fields in a distant galaxy subtly twist the polarization of radio waves passing through them, allowing scientists to map the field's strength and direction. Our own Milky Way provides a stunning case study. Its magnetic field is not a simple, large-scale bar magnet. It is a chaotic tapestry, with its overall direction loosely aligned along the spiral arms and punctuated by enormous bubbles and loops blown out by the supermassive black hole at our galaxy's center. This intricate structure reveals a dynamic history of stellar winds, supernova shocks, and galactic fountains, all working together to shape the magnetic landscape we inhabit. So where did it all begin? Did these fields emerge from the quantum foam of the universe's first instant, a fundamental part of creation itself? Or are they a later byproduct, an inevitable consequence of cosmic structure formation, emerging as galaxies themselves began to coalesce? This mystery of cosmic magnetism highlights a profound interconnectedness. It shows that forces we once thought were local, confined to planets and stars, are in fact written across the vast, dark canvas of the universe, governing the flow of matter and energy on the grandest scales. Even the quietest moment is punctuated by an invisible rain. Subatomic particles from deep space, known as cosmic rays, constantly bombard our planet. Most are low-energy protons, but a rare few carry an almost unbelievable punch. These are ultra-high-energy cosmic rays, single particles with energies exceeding 10 to the 20th power electron volts. Each one carries the kinetic energy of a professionally thrown baseball, all compressed into a single, microscopic projectile. The existence of such particles is a profound cosmic puzzle. According to our understanding of physics, they should not be able to travel very far across the universe. The space between galaxies is not completely empty. It is filled with the faint relic radiation from the Big Bang, the cosmic microwave background. A proton traveling at such an insane speed would constantly bump into these background photons, losing energy with every collision over distances greater than about 150 million light-years. This is known as the GZK Cutoff, yet we detect them anyway. As physicist Jim Cronin stated, the origin of the highest energy cosmic rays is one of the great mysteries in astrophysics. So what cosmic engines are powerful enough to accelerate particles to these extreme energies, and how are they reaching us? The suspects are the most violent phenomena in the universe. Active galactic nuclei, where matter spirals into supermassive black holes, can launch jets of plasma stretching for millions of light-years. These jets could act as natural particle accelerators on a staggering scale. Another candidate is the cataclysmic collapse of massive stars in gamma-ray bursts, events that release more energy in seconds than our Sun will in its entire lifetime. More exotic possibilities include the decay or annihilation of hypothetical super-heavy dark matter particles, a process that could release immense energy in the halos of galaxies. The challenge is not just identifying the source, but actually tracing a particle back to its origin. Cosmic rays are charged, so their paths are bent and scrambled by the interstellar and intergalactic magnetic fields they pass through. By the time one reaches Earth, it is impossible to point backwards and see exactly where it came from. To study them, we do not catch the particles directly. Instead, giant observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah watch for the secondary effects. When an ultra-high-energy cosmic ray slams into the top of our atmosphere, it creates a spectacular cascade of billions of secondary particles, an air shower that spreads for miles. Detectors spread across vast areas of desert capture these showers, allowing scientists to reconstruct the energy and direction of the original primary particle. The most famous example of this enigma is the so-called "Oh my God" particle, detected over Utah in 1991. Its energy was so phenomenally high that it defied belief, and its origin remains completely unknown to this day. Could these cosmic bullets be messengers from an entirely new class of astrophysical object, one we have not yet discovered? Or might they even be a sign of new physics, a crack in our understanding of how particles and fields interact across the vastest distances? They represent nature's ultimate particle accelerators, far surpassing anything we can build on Earth, and their secrets are written in the faint, fleeting flashes of light they leave in our own sky. Gravity is the quietest voice in the cosmic conversation, a faint whisper lost in a room of shouting. The force that holds entire galaxies together is a staggering 10 to the 36 times weaker than the electromagnetic force that binds atoms. You can feel this every time you lift a paperclip with a small magnet, effortlessly defeating the gravitational pull of the entire Earth. This immense disparity is known as the hierarchy problem, and it points to a deep crack in our understanding of the fundamental ingredients of reality. At its heart is the Higgs boson, the particle that gives all others mass. The problem is its measured mass, 125 gigaelectronvolts, is unnaturally light. In the quantum world, the Higgs mass should be constantly tugged and corrected by its interactions with every other particle, pulling its value up to the Planck scale, the enormously high energy where gravity becomes strong. This would make the Higgs mass about a quadrillion times heavier than what we observe. So why is it so lightweight? Is the universe fine-tuned with absurd precision? Or is some hidden mechanism protecting the Higgs from these quantum corrections? Theorist Nima Arkani-Hamed has stated that the hierarchy problem points to something profound we are missing. One of the most elegant proposed solutions is supersymmetry. This theory posits that every known particle has a hidden superpartner. For every electron, there would be a selectron. For every quark, a squark. These superpartners would perfectly cancel out the quantum corrections pulling on the Higgs mass, naturally explaining its lightness. If supersymmetry were true, it would also provide a perfect candidate for dark matter. Yet, despite decades of searching, the Large Hadron Collider has found no evidence for these superpartners. The Higgs mass was measured, and the new physics simply did not appear. Another radical idea involves the very nature of gravity itself. Perhaps gravity is not inherently weak. Maybe it only appears feeble because it is leaking into hidden, extra dimensions of space that are curled up at scales far smaller than an atom. In this scenario, the full strength of gravity is diluted as it spreads into these unseen realms, leaving only a faint shadow of its true power in our familiar three-dimensional world. The fact that the LHC found the Higgs boson exactly where it was, with no accompanying signs of supersymmetry or extra dimensions, has only deepened the mystery. It leaves us with haunting questions. Is the hierarchy of forces a colossal cosmic accident, a random roll of the dice in our particular pocket of reality? Could it be evidence for the multiverse, where in an infinite tapestry of universes with different laws and constants, we just happen to live in one where the values are improbably right for atoms, planets, and life to exist? This single puzzle bridges the smallest scales of particle physics with the largest questions of cosmology, forcing us to confront whether our universe is finely tuned for a reason, or if we are simply the beneficiaries of a staggering, unexplained coincidence. An entire encyclopedia of knowledge could vanish from our universe without a trace. If you were to throw one into a black hole, it would cross the event horizon, that point of no return, and seem to be lost forever. Yet, according to the fundamental rules of quantum mechanics, information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This creates a terrifying contradiction at the heart of physics. Stephen Hawking first exposed this paradox in the 1970s. he realized that black holes are not completely black. They slowly evaporate by emitting a faint glow of particles, now known as Hawking radiation. His initial calculations suggested this radiation was purely thermal, a featureless hiss carrying no information about what fell in. If the black hole eventually evaporates completely, then all the information about that encyclopedia and everything else it consumed would be permanently erased from reality. As physicist Leonard Susskind explains, the information paradox forces us to reconcile gravity with quantum mechanics. For decades, this was the greatest crisis in theoretical physics. The solution may lie in one of the most revolutionary ideas of all time, the holographic principle. This concept suggests that all the information contained within the three-dimensional volume of a black hole is actually encoded on its two-dimensional event horizon, like a cosmic fingerprint. The information is not destroyed, it is smeared across the surface. When Hawking radiation is emitted, it slowly and subtly carries that encoded information back out into the universe. This leads to another dizzying puzzle, the firewall paradox. If information is leaking out from the event horizon, does that mean the horizon is not the smooth, empty space predicted by general relativity, but a searing wall of high-energy particles that would incinerate anything falling in? We are forced to choose between violating Einstein's equivalence principle, a cornerstone of general relativity, or violating quantum unitarity, the law that information must be preserved. The most promising framework for a solution comes from string theory, through a concept called the AD-S/CFT correspondence. This is a mathematical duality that proposes a universe with gravity in its interior is completely equivalent to a quantum field theory without gravity living on its boundary. It is like discovering that a movie playing in a vast theater is exactly the same as the two-dimensional code on the DVD it is being played from. The information is never lost, it is just translated from one language to another. Recent work on entanglement entropy, the deep quantum connections between particles, suggests that the interior of a black hole and its Hawking radiation are intricately linked, forming a bridge that allows information to escape. So where does that leave our encyclopedia? Is every letter and diagram slowly, painstakingly radiated back into the cosmos over billions of years, imprinted onto the particles that flee the black hole's grip? Or does the very existence of this paradox mean that space-time itself is not fundamental, but an emergent property of a deeper quantum reality? The fate of information falling into a black hole is not just about cosmic bookkeeping. It is a direct assault on our understanding of reality, forcing us to ask if the world we perceive is merely a projection, a hologram born from information stored at the boundaries of our perception. The theoretical vacuum should be screaming with energy, yet we observe only a whisper. This is the cosmological constant problem, arguably the single greatest failure of theoretical prediction in all of science. Quantum field theory, our most successful framework for describing particles and forces, calculates the energy density of empty space by summing up all the fleeting quantum fluctuations. The result is a number so colossal it defies reason, a value of 10 to the 120th power larger than the tiny, positive value we actually measure from the accelerating expansion of the cosmos. To get the observed universe, the theoretical calculation must be wrong by a factor of 1 followed by 120 zeros. It is as if you calculated the weight of the entire ocean, but when you dipped a cup into the water, you found only a single, solitary molecule. Physicist Steven Weinberg called this discrepancy not just a problem, but a genuine crisis for fundamental physics. The universe seems to be fine-tuned to an almost absurd degree. The cosmological constant, or the energy of the vacuum, must be balanced with an unimaginable precision, cancelling out nearly all of its own inherent energy to leave behind the minuscule residue we call dark energy. This staggering fine-tuning forces us to confront two deeply unsettling possibilities. The first is the anthropic argument. Perhaps the cosmological constant is not determined by a fundamental law, but can vary from one universe to another in a vast multiverse. In this cosmic landscape, only in the rare pockets where the constant is almost exactly zero can galaxies, stars, and life ever form. We exist, therefore we must live in one of those exceptionally rare, finely tuned universes. String theory offers a potential home for this idea, suggesting a landscape of perhaps 10 to the 500 possible vacuum states, each with different physical constants. Our universe would just be one island in this incomprehensibly vast archipelago, one where the numbers accidentally allow for our existence. The alternative is to hope for a dynamical mechanism that naturally cancels the vacuum energy. Perhaps dark energy is not a constant at all, but a slowly evolving field like quintessence that has dynamically relaxed to its current small value over billions of years. Or maybe there is a deep symmetry we have not yet discovered, a principle that forces the vacuum energy to be exactly zero, with dark energy arising from something else entirely. Yet every observation, from distant supernova to the cosmic microwave background, keeps pointing back to a cosmological constant that is small, positive, and stubbornly constant. So we are left with a profound choice. Is our universe one of unimaginable rarity, a statistical fluke in a multiverse of dead, lifeless voids? Or is the vacuum itself trying to tell us that our theories of quantum fields and gravity are fundamentally incompatible, missing a crucial piece that would resolve this embarrassing contradiction? The whisper of dark energy may be the quietest clue to the deepest flaw in our understanding of reality. Our universe is supposed to be a grand, featureless expanse with no center and no preferred direction. Yet a ghostly alignment in the oldest light we can see seems to point a finger directly at our own cosmic neighborhood. This is the axis of evil, a pattern in the cosmic microwave background that eerily correlates with the plane of our solar system. Discovered in data from the WMAP satellite and later confirmed by Planck, this anomaly shows that the largest fluctuations in the infant universe are not randomly scattered. Instead, they appear to be aligned along a particular axis, one that suspiciously matches our ecliptic plane. Cosmologist Joanna Dunkley acknowledges these alignments are puzzling and could indicate unknown systematics or new physics. This is not just a minor statistical quirk, it strikes at the heart of the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, looking the same in every direction from any vantage point. The data reveal two specific oddities. The first is a strange alignment of the quadrupole and octupole moments, the patterns that describe the universe's largest possible waves. The second is an unexpectedly low power in these largest scales, as if something suppressed the biggest ripples in spacetime. Imagine throwing a handful of pebbles into a pond and seeing all the largest ripples line up in the same direction, pointing back at you. That is the level of strangeness we are confronting. So what could be causing this? The most conservative explanation is a local contaminant, some foreground effect from within our own Milky Way that we have not perfectly subtracted from the data. Perhaps dust or magnetic fields are imprinting a pattern we mistakenly attribute to the primordial universe. Another possibility involves the gravitational influence of nearby structures, a cosmic tidal force that gently tugs on the CMB. But the most thrilling possibility is that this is a genuine crack in our standard model, a fossil from a time before the Big Bang. Some theories of a cyclic universe, where our Big Bang was preceded by a previous cosmic phase, predict such a preferred direction could be imprinted on the new creation. Could it be that the axis of evil is not an error, but a shadow of a previous cosmos, a memory of a universe that came before our own? This forces a deeply unsettling question about our place in the cosmos. The Copernican principle taught us we are not at the center of the universe. But what if we are not in a random location either? What if the very structure of reality has a grain to it, and we just happen to see that grain aligned with our own small corner of space? This single anomaly connects to other large-scale mysteries, from the mysterious cold spot to the hemispheric power asymmetry, suggesting our smooth, uniform universe might be built on a foundation that is subtly lopsided. Is this alignment a monumental fluke, a trick of incomplete data, or is it the first faint whisper of a cosmos far stranger and more structured than we ever dared believe? The universe's first recipe was remarkably simple. In the initial fiery minutes after the Big Bang, nuclear fusion cooked the primordial soup of protons and neutrons into the lightest elements, a process known as Big Bang nucleosynthesis. The theoretical calculations are precise, predicting that about 75% of the ordinary matter should be hydrogen, nearly 25% helium, and a tiny trace of lithium. Yet when astronomers search for this ancient lithium in the oldest stars in our galaxy, they find only about a third of the expected amount. This persistent mismatch is the Lithium Problem, a quiet but glaring discrepancy that has endured for decades. Astrophysicist Brian Field summarizes it perfectly, stating that the Lithium Problem is a clear signal that our understanding of early universe physics is incomplete. The evidence for this shortfall is etched in the light of ancient, metal-poor stars that dwell in the halo of our Milky Way. These stellar relics are so old that their composition reflects the pristine conditions of the early cosmos. When scientists analyze their spectra, they find a consistent low level of lithium, a feature known as the Spite Plateau after the astronomers who discovered it. This plateau is the smoking gun, showing that the lithium deficit is a primordial problem, not something that developed later. So where did the lithium go? The hunt for an answer has led physicists down several intriguing paths. Perhaps our models of the nuclear reaction rates during those first few minutes are slightly off. A tiny adjustment to how quickly certain isotopes fused could resolve the discrepancy. Another possibility involves new physics beyond the standard model. Exotic particles, such as certain types of dark matter, could have been present in the early universe, altering the nuclear reactions as they decayed or interacted with normal matter. Or maybe the solution lies not in the bang itself, but in the stars. Could these ancient stars themselves be destroying lithium over their immensely long lives, dragging it from their outer atmospheres down into their hot interiors where it is fused into heavier elements? This puzzle is uniquely powerful because it ties together two seemingly independent pillars of modern cosmology. The baryon density of the universe, a key number that describes the total amount of ordinary matter, is measured with high precision from the cosmic microwave background. When we plug this exact same number into the equations for Big Bang nucleosynthesis, it predicts a specific amount of lithium that should exist today, a prediction that stubbornly disagrees with what we see in the stars. This forces us to ask a profound question. Is the universe hiding an unknown nuclear pathway, or could a fleeting, undiscovered particle have subtly rewritten the cosmic recipe in its first moments? The missing lithium is a small but crucial clue, a single wrong ingredient that hints at a much larger story unfolding between particle physics and the life cycles of the earliest stars. A vast cosmic river is pulling us inexorably toward the unknown, Our Milky Way, along with countless other galaxies, is caught in this immense flow, all drifting toward a specific point in the darkness near the constellation Centaurus. This mysterious destination is known as the Great Attractor, a gravitational anomaly so powerful it commands the motion of an entire galactic neighborhood. Astronomer Lister Stavely Smith confirms the challenge, noting the Great Attractor remains shrouded in dust, making it difficult to study. This hidden powerhouse is estimated to contain the mass of tens of thousands of galaxies, a concentration of matter so vast it warps the very fabric of local space. We can sense its pull not by seeing it directly, but by watching how other galaxies move. Their paths are not perfectly smooth. By comparing a galaxy's redshift, which tells us how fast the universe's expansion is carrying it away, with its actual measured distance, astronomers discover a discrepancy known as its peculiar velocity. This is the galaxy's true motion through space, a drift superimposed on the cosmic expansion. It is these peculiar velocities that trace out the invisible currents flowing toward the Great Attractor. Our own local group of galaxies is racing toward this point at a breathtaking 600 kilometers per second. This grand picture places the Great Attractor in a wider context, as the gravitational heart of an even larger structure we belong to, the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, is a cosmic filament containing over 100,000 galaxies, all flowing toward this same central valley. The core of the Great Attractor lies directly behind the crowded, dusty plain of our own Milky Way, a region astronomers call the Zone of Avoidance. Our galaxy's own starlight and cosmic dust block our optical view, creating a blind spot in the sky. To peer through this obscuring veil, scientists turn to instruments that see in other parts of the spectrum. Infrared telescopes can cut through the dust, and radio telescopes map the distribution of hydrogen gas, revealing the hidden galaxies that constitute this colossal mass. So what lies at the heart of this immense gravitational pull? Is it an exceptionally dense knot of dark matter, a supercluster of unprecedented scale, or could it be something even more unusual, a structural flaw in the expanding universe itself? This puzzle forces us to map the invisible architecture of the cosmos, reminding us that even the grandest motions of the heavens are governed by the silent, unseen hand of mass. Between the glowing filaments of the cosmic web stretch immense, silent bubbles of near-nothingness. These are cosmic voids, regions spanning hundreds of millions of light years where galaxies are scarce and the darkness is profound. If you think of the universe's structure as a vast cosmic foam, these voids are the empty spaces within it, making up the overwhelming majority of the universe's volume. Yet their profound emptiness is a puzzle in itself. How did such vast regions come to be so empty, and what do these great deserts tell us about the forces shaping the cosmos? Cosmologist Laura Mersini-Horton offers a key insight, stating that voids are not just empty space, they hold clues to dark energy and inflation. Their formation is a story that begins with the tiniest of seeds. In the infant universe, slight underdensities, regions with just a little less matter than their surroundings, were imprinted by inflation. As the cosmos evolved, gravity acted as a cosmic real estate agent, pulling matter out of these underdense regions and into the denser filaments and nodes of the cosmic web. The voids were left behind, growing emptier and larger over billions of years, but their evolution does not stop there. Dark energy, the mysterious force driving cosmic acceleration, finds its greatest influence in these empty realms. With so little matter to provide gravitational pull, dark energy's repulsive effect dominates, pushing the void walls ever farther apart and accelerating their expansion. Astronomers map these incredible structures using massive galaxy surveys like the Sloan Digital Sky Survey. which painstakingly charts the positions of millions of galaxies to reveal the void network's true scale and geometry. One of the most famous examples is the Boötes void, a spherical emptiness so vast it could contain thousands of galaxies like our Milky Way, yet hosts only a handful. The emptiness is not perfect. A few lonely galaxies do drift in this incredible darkness, but their presence only deepens the mystery of how such a void could form. We can even sense the influence of these voids through their effect on the oldest light in the universe. As photons from the cosmic microwave background travel through an expanding void, they must climb out of its gravitational well, losing a tiny amount of energy in a process called the integrated Sachs-Wolfe effect. This subtle imprint on the CMB provides independent confirmation that these vast empty regions are real, and that their gravitational pull, or lack thereof, shapes the light traversing the cosmos. So, what do these great cosmic bubbles ultimately reveal? Are they pristine laboratories where the properties of dark energy can be measured free from the clutter of galaxies? Or could their very existence and rapid growth be a sign that gravity itself behaves differently in these near-empty realms, a hint of modified gravity on the largest scales? The void phenomenon forces us to confront the universe's large-scale topology, reminding us that to understand the glittering structures of the cosmic web, we must first understand the profound emptiness that defines them. Sometimes the most profound mysteries are solved not by discovering something new, but by looking more closely at what we already have. The twin Pioneer spacecraft, 10 and 11, became the focus of one such puzzle after they completed their primary missions to Jupiter and Saturn. As they sailed into the dark, their trajectories were tracked with exquisite precision, revealing a tiny, persistent drift. Each probe was experiencing a constant, sunward acceleration, a subtle pull back toward the inner solar system that existing models of gravity and spacecraft motion could not explain. This was the Pioneer Anomaly, a whisper of a force with a magnitude of just about 8.74 times 10 to the negative 10 meters per second squared. For years, this unexplained nudge fueled speculation. Could it be a sign of modified gravity, a flaw in Einstein's theory of general relativity that only became apparent in the vast emptiness of the outer solar system? Perhaps it was the gravitational tug of unseen dark matter concentrated near our Sun. The anomaly was a siren call for new physics, a tantalizing hint that our cosmic rulebook was missing a page. Physicist Slava Turyshev, who led the intensive investigation into the mystery, later reflected that the Pioneer Anomaly taught us the importance of meticulous modeling. His team embarked on a monumental effort to reconstruct the entire life history of the Pioneer probes, recovering decades-old data and building new software models of the spacecraft themselves. The breakthrough came not from deep space but from a careful accounting of heat. The probes were powered by radioactive thermoelectric generators, which produced heat that was radiated away from the spacecraft. The team realized that a tiny, anisotropic effect, a slight imbalance in how this thermal radiation was emitted, could provide the necessary push. Photons carrying heat away from the craft would impart a minuscule recoil, and if this recoil was not perfectly symmetrical, it could create a net force. The detailed analysis confirmed it. The very gentle pressure of infrared photons bouncing off the spacecraft structure was the unseen hand guiding the Pioneers. This conventional explanation, once all the complex thermal properties were accounted for, completely resolved the anomaly. The story of the Pioneer probes serves as a vital lesson for missions like New Horizons, which now travels through the Kuiper belt. Its trajectory is monitored with even greater care, its thermal emissions modeled from the start to avoid a similar decades-long puzzle. So how often do these cosmic anomalies lead to genuine breakthroughs versus instructive dead ends? The Pioneer Anomaly stands as a beautiful cautionary tale, a reminder that the universe often hides its secrets not in grand new forces, but in the overlooked details of the machines we send to explore it. Before we proclaim a revolution in physics, we must first ensure we have not simply left a light on. A spacecraft's path is a carefully calculated dance, but sometimes the universe changes the music. When probes like Galileo and the Near-Earth Asteroid Rendezvous mission, or NEAR, swung past Earth for a gravity assist, they experienced something strange. Their velocities shifted by a few millimeters per second, a tiny but consistent deviation from the precise predictions of orbital mechanics. These unexpected gains and losses of speed during planetary flybys became known as the Flyby Anomaly. Aerospace engineer John Anderson noted that this small effect carries big implications for our fundamental physics. For a field that relies on perfect precision to navigate the solar system, even a minuscule, unaccounted-for nudge is a major concern. The anomaly was detected through the meticulous tracking of radio signals. As a spacecraft speeds away from Earth, the frequency of its signals shifts due to the Doppler effect, much like the changing pitch of a siren passing by. By analyzing this shift, engineers can measure velocity with incredible accuracy, revealing these perplexing discrepancies. Scientists have explored every conventional explanation. Could residual atmospheric drag at high altitudes be the culprit? What about the subtle influence of Earth's rotation, or the esoteric effect of frame dragging, where our planet's spin gently tugs on the fabric of space-time itself? Yet none of these factors, even when combined, fully explain the observed data. The mystery only deepened with the Rosetta spacecraft. During its own Earth flyby, mission controllers watched closely, expecting to see the same anomaly. Instead, Rosetta's speed matched the predictions perfectly. Why would some spacecraft experience this effect while others do not? This selective nature of the anomaly points away from a simple, universal cause. It forces us to consider more exotic possibilities. Could it be a sign of modified inertia, where our understanding of how objects move breaks down under very specific conditions? Or is there an unseen component to Earth's gravitational field, a hidden structure we have not yet mapped? Each unplanned millimeter per second is a quiet challenge to the laws we thought governed our celestial neighborhood. It reminds us that our maps of the solar system, for all their detail, may still have uncharted territories, places where gravity behaves in ways we have yet to comprehend. Our own cosmic address may be far more unusual than we ever suspected. The Milky Way appears to float not in an average region of space, but within an immense, spherical bubble of relative emptiness, a void spanning an almost unimaginable 2 billion light-years across. This proposed structure, known as the KBC Void after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, suggests our galactic home sits inside a vast underdensity where the number of galaxies is significantly lower than the cosmic average. If confirmed, this local hole would present a direct challenge to the cosmological principle, the foundational idea that the universe is smooth and homogeneous on the largest scales. As astronomer Amy Barger notes, the KBC void could alter our interpretation of dark energy measurements. The evidence for this great local emptiness comes from painstakingly counting galaxies and measuring the distances to supernova. These observations consistently suggest that the density of matter in our cosmic neighborhood is roughly 20 to 50% lower than the universal average, creating a local deficit of gravity. Within such a void, the cosmic expansion would proceed slightly faster than in the denser regions outside, because there is less gravitational pull to slow it down. This creates a critical puzzle for cosmologists. Could our local measurement of the Hubble constant, the rate of the universe's expansion, be artificially high simply because we are living inside a giant bubble? The conflicting results from different astronomical surveys keep this puzzle alive. Some studies of galaxy distributions strongly support the existence of the KBC void, while others, looking at different celestial traces, find the local universe to be far more average. The debate hinges on whether this apparent underdensity is a real, physical structure or merely a colossal statistical fluke, a rare but possible quiet patch in an otherwise uniform cosmos. This enigma forces a deeply philosophical question. Are we, against all Copernican wisdom, in a special place after all? The answer lies in the meticulous work of mapping the universe on the grandest possible scale, charting the true distribution of galaxies to see if our local void is a cosmic anomaly or a common feature of the vast invisible web. Light from the farthest reaches of the cosmos carries a hidden pattern. Across billions of light-years, the polarization axes of light from quasars, the brilliant cores of active galaxies, show a startling coherence. They are not randomly oriented as standard physics would predict. Instead, these ghostly imprints of electromagnetic direction seem to align with one another over mind-bogglingly vast distances, suggesting the universe itself might have a subtle grain, a preferred direction woven into its fabric. This discovery of large-scale correlations in quasar polarization is a profound anomaly, one that astronomer Damian Hatzimakers states clearly points to something beyond our current models. To understand this, picture polarization as the specific direction in which a light wave oscillates. When light from a quasar travels through the cosmos, its polarization can be measured using specialized filters on optical telescopes or by analyzing radio waves. The shock comes when scientists plot the positions of thousands of these quasars on a map and then draw lines indicating their individual polarization angles. The result is not a chaotic scribble. In certain regions of the sky, the lines show a surprising degree of alignment, as if an invisible hand has gently combed them in a similar direction. The statistical analyses confirm this is not a fluke. The probability of such coherence arising by random chance is incredibly small. What cosmic force could possibly orchestrate this? One compelling theory points to the influence of universal magnetic fields. Perhaps these alignments are tracing the lines of a primordial magnetic field that permeates the entire universe, a fossil from its earliest moments that gently twists the polarization of light traveling through it. Another, more exotic idea involves new fundamental fields, such as action-like particles. These hypothetical particles could interact with light as it journeys across the cosmos, gradually rotating its polarization plane in a coordinated way. This puzzle feels eerily familiar, connecting directly to other large-scale anomalies like the axis of evil in the cosmic microwave background. Are we seeing multiple signatures of a fundamentally anisotropic universe, one that is not the same in every direction? Or could this all be a monumental illusion, an artifact of how we observe the cosmos or an unknown local effect within our own galactic neighborhood? The alignment of quasar polarization forces us to confront the nature of light propagation and the invisible architecture of space itself, hinting that unified cosmic fields, yet to be discovered, are guiding the very light we use to see. Even our cosmic accounting has a major shortfall. The universe's ledger of ordinary matter is badly out of balance. According to the precise recipe from Big Bang nucleosynthesis and confirmed by the cosmic microwave background, we know exactly how many protons and neutrons, the baryons that make up every atom, should exist. Yet when we tally up all the visible matter in stars, galaxies, and the cool gas nearby, we find only about half the expected amount. Billions of solar masses of ordinary atoms seem to have vanished without a trace. This is the missing baryons problem, and it forces us to ask a simple, startling question. Where did half the atoms in the universe go? Astrophysicist Michael Schull offers the leading clue, stating that the missing baryons are hiding in the cosmic web's filaments. The prime suspect is not a mysterious substance, but ordinary matter in an elusive form, a diffuse, superheated gas known as the warm-hot intergalactic medium, or WIM. This gas is thought to be threaded through the vast filaments of dark matter that connect galaxies, a cosmic plumbing system too hot and thin to glow brightly, but too tenuous to cast a clear shadow. Detecting this ghostly web is one of astronomy's greatest technical challenges. Scientists hunt for it using the light of distant quasars as cosmic flashlights. As this brilliant light travels billions of light years to reach us, it passes through the filaments of the WIM. Atoms within that gas, like oxygen and neon, absorb specific wavelengths of the quasar's light, leaving behind a unique fingerprint, a series of tiny, dark lines in the spectrum. These absorption lines, particularly in the ultraviolet and X-ray parts of the spectrum, are the telltale signatures of this hidden matter. Supercomputer simulations of cosmic structure formation paint a vivid picture of where to look. They show that as galaxies form, powerful shocks and galactic winds heat the surrounding gas, pumping energy into these intergalactic filaments and raising their temperature to hundreds of thousands, even millions of degrees. It is in these vast, invisible rivers of hot gas that the missing baryons are predicted to reside. The hunt has already scored some successes. Observations from the Hubble Space Telescope have detected absorption from highly ionized oxygen, known as OVI, in the ultraviolet. Meanwhile, NASA Chandra X-ray Observatory has found hints of the even hotter gas through absorption lines from other ions. With each new observation, the missing fraction of baryons shrinks, yet a stubborn gap remains. The difficulty is that this gas is so diffuse that its absorption signal is incredibly faint, like trying to spot a single, thin cloud by the shadow it casts from a star 1,000 light-years away. What new technique will finally allow us to see this cosmic plumbing in its entirety? Could more sensitive X-ray observatories, or perhaps a census of thousands of quasars, finally close the cosmic ledger? This puzzle reminds us that the universe's most fundamental ingredients can hide in plain sight, not as dark matter, but as a faint, hot breath lingering in the spaces between the galaxies. A flash of radio light brighter than 500 million suns vanishes in less than a blink. These are fast radio bursts, or FRB, millisecond-long pulses of cosmic energy that appear without warning from the distant depths of space. In that fleeting instant, a single burst can release as much energy as our sun puts out over several days. Astronomer Duncan Lorimer, who helped bring them to light, calls them a new window into the universe's most extreme events. The sheer violence and brevity of these signals point to environments where physics is pushed to its absolute limit. The hunt to pinpoint their origins has led scientists to some of the most exotic objects known. One leading suspect is the magnetar, a type of neutron star with a magnetic field so powerful it could erase a credit card from half the distance to the moon. A starquake on such an object, a sudden cracking of its rigid crust, could unleash a firestorm of radio waves. Another possibility is the catastrophic collision of two neutron stars, merging in a shroud of dense, magnetized debris. Or perhaps the source is something entirely new, a theoretical object like a blitzar, a supermassive neutron star that narrowly avoided collapsing into a black hole. The true breakthrough in this mystery came with the discovery of repeaters. While most FRBs are one-off events, a few, like the famous FRB 121102, flash again and again in unpredictable patterns. This repetition ruled out any source that destroys itself, like a single, final collision. By tracing the repeating flashes of FRB 121102 back to their host, astronomers were stunned to find it originated in a tiny, rambunctious dwarf galaxy, a place buzzing with the furious birth of new stars. This specific environment strongly suggests a connection to young, highly magnetic neutron stars. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, now scan the sky continuously, catching hundreds of these events and mapping them to their host galaxies across cosmic time. Each new detection adds a piece to the puzzle, but the central question remains: what natural engine can power such intense, focused, and sometimes repeating explosions? Could we even be witnessing the collapse of cosmic strings or other phenomena from the very edge of theoretical physics? The signals themselves are more than just messages from violent events. As they travel across billions of light-years, they pass through the diffuse gas between galaxies. This material subtly stretches and distorts the radio waves, and by measuring this effect, astronomers can use FRBs as probes to weigh the universe's missing ordinary matter, the very baryons that have eluded our direct sight. This dual nature makes them both a profound mystery and a powerful new tool. So we are left to wonder, are these brilliant flashes the final death cries of collapsing stellar corpses, or could they, against all odds, be the first faint signatures of an advanced civilization manipulating energies we can barely comprehend? Each pulse from the dark is a question, challenging our definitions of what is possible in the cosmos and urging us to listen more closely to the silent radio sky. A classic cosmic test is revealing a subtle but persistent disagreement. Decades ago, physicist Richard Tolman proposed an elegant way to confirm the expansion of the universe. He reasoned that in a truly expanding cosmos, the surface brightness of a galaxy, its light spread across its apparent size, should fade dramatically with distance. This dimming happens for two key reasons. The expansion of space stretches the light waves, making each photon less energetic, and it also dilutes the arrival rate of those photons. Combined, these effects mean a distant galaxy's surface brightness should plummet as the fourth power of 1 plus its redshift. Yet when astronomers perform this test, the observations are ambiguous. As cosmologist Eric Lerner has argued, the Tolman test might indicate tired light or other alternatives. Some analyses of galaxy clusters show less dimming than the expanding universe model predicts. The data seem to suggest these ancient islands of stars are brighter than they have any right to be. This is not a simple measurement to make. The test is profoundly complicated by galaxy evolution. A distant galaxy is also a young galaxy, and its stars were often brighter, hotter, and more densely packed than those in modern galaxies. Untangling the effects of cosmic expansion from the intrinsic changes in the galaxies themselves is a monumental task. Researchers have turned to the deepest views of the cosmos, like the Hubble Ultra Deep Field, analyzing thousands of galaxies to see if their collective dimming matches the theoretical curve. The results remain mixed, with some studies claiming a clear confirmation of the standard model and others pointing to a significant deviation. This forces a fundamental question. Is the redshift of light truly a metric effect, a stretching of space itself, or could it be caused by something else, like the hypothetical tired light mechanism where photons gradually lose energy during their long journey through a faintly absorbing medium? The Tolman test strikes at the very heart of our cosmological framework. challenging us to prove that the redshift we measure is truly a measure of cosmic velocity and not a sign of a more complex, unexplained process. The theoretical wall is real, but the cosmic bullets keep coming. The Greisen-Zatsepin-Kuzmin cutoff, or GZK cutoff, stands as a firm prediction in physics, a fundamental energy limit for particles traveling across the universe. According to this rule, any proton with an energy greater than 5 times 10 to the 19th electron volts should be unable to journey more than about 150 million light-years. Such a particle, moving at a hair's breadth from the speed of light, would inevitably collide with the photons of the cosmic microwave background, the cold relic radiation filling all of space. Each collision would rip the proton apart in a process called photopion production, sapping its energy until it falls below the limit. The universe, in effect, has a built-in speed bump for its most energetic travelers. Yet our detectors tell a different story. We consistently observe cosmic rays with energies soaring far beyond this supposed ceiling. Physicist Glenys Farrar puts it plainly, stating that the GZK puzzle challenges our understanding of particle propagation. The data from the Pierre-Auger Observatory and the telescope array show a cosmic ray spectrum that does not feature the sharp drop-off we expect. Instead, the plot of energy versus frequency shows a smooth curve with a gentle bend, a feature astronomers call the ankle, but the expected catastrophic cutoff is conspicuously absent. This forces a radical question. Are these ultra-high energy particles not coming from vast distances, but from relatively nearby sources within our local cosmic neighborhood where they have not had time to be slowed down? If so, what incredibly powerful and nearby object is acting as a natural accelerator? The search for sources within this GZK horizon has so far been inconclusive, with no clear galaxies or violent events pointing directly back to these arrivals. The other, more thrilling possibility is that we are witnessing a failure of our fundamental physics. Could it be that Lorentz invariance, a cornerstone of Einstein's special relativity that dictates how particles behave at such high speeds, is not an absolute law? Perhaps at these extreme energies, the rules subtly change, allowing particles to travel farther than they ever should. This enigma probes the very extremes of astrophysics and fundamental symmetries, asking us if the universe's ultimate speed limits are not what we thought, and if the particles screaming through the void are messengers of a deeper law yet to be written. Our two most successful theories of reality are locked in a fundamental standoff. One governs the universe on its grandest stages, the other dictates the rules of the smallest possible realms, and they refuse to speak the same language. This is the quantum gravity conundrum, the deep incompatibility between Einstein's general relativity and quantum mechanics. General relativity paints a picture of smooth, continuous spacetime, a flexible fabric warped by mass and energy. Quantum theory, in stark contrast, reveals a microscopic world of discrete packets, probabilities, and frenetic uncertainty. When these two ideas are forced together, the mathematics breaks down into nonsensical infinities, particularly at the unimaginably tiny Planck scale. Physicist Carlo Rovelli offers a guiding light, stating that quantum gravity is the key to understanding the beginning of the universe. The quest for a theory that unites them is the holy grail of modern physics, and the candidates are as bold as they are bizarre. String theory proposes that the fundamental constituents are not point particles, but tiny, vibrating loops of energy. Their various resonant frequencies could give rise to all the particles and forces, with gravity naturally emerging from the mix. This elegant idea, however, often requires the existence of 7 hidden spatial dimensions beyond our perception. Loop quantum gravity takes a different path, suggesting that space itself is not smooth, but woven from a network of discrete, finite loops. In this view, spacetime has a granular, atom-like structure, resolving the infinities by positing a smallest possible unit of area and volume. A third contender, asymptotically safe gravity, argues that gravity might be a consistent quantum theory all on its own if its strength changes with energy scale in just the right way. The challenges are profound. Gravity is notoriously non-renormalizable, meaning its quantum corrections spiral out of control. There is also the deep philosophical problem of time, where the absolute flowing time of general relativity clashes with the static, probabilistic time of quantum mechanics. So how can we test these ethereal ideas? The collisions of black holes observed by LIGO provide one crucial laboratory. The gravitational waves they emit so far match the predictions of general relativity perfectly. But future, more sensitive detectors might spot subtle deviations in the ringing of the newborn black hole, a signature of quantum structure at the event horizon. The earliest moments of cosmic inflation are another testing ground, where quantum gravity effects could have left an imprint on the pattern of galaxies we see today. Even tabletop experiments are joining the hunt, using supercold atoms or entangled systems to probe whether spacetime itself exhibits quantum properties. Will the ultimate theory reveal a universe built from vibrating strings in a higher dimensional arena? Or will we find that space and time are fundamentally pixelated, emerging from a web of quantum connections? This single puzzle underpins all others, for a true theory of quantum gravity would not only tell us what happened at the very first moment of the Big Bang, but could also finally unlock the secrets of dark energy, the information paradox, and the ultimate fate of our cosmos. Our cosmos could be a single bubble in an endless, frothing sea. The multiverse hypothesis suggests our universe is just one of countless others, each with its own unique set of physical laws and constants. Some might have stronger gravity, rendering stars unstable. Others might lack electromagnetism, preventing atoms from ever forming. In this grand tapestry, a universe like ours, finely tuned for complexity and life, becomes statistically inevitable rather than astronomically improbable. Cosmologist Max Tegmark offers a compelling perspective, stating that the multiverse offers a natural explanation for why our universe is the way it is. The theory arises naturally from two of our most powerful frameworks. Eternal inflation proposes that the rapid expansion of spacetime never truly stopped, but instead continues eternally, giving birth to new bubble universes in a limitless cosmic foam. Meanwhile, string theory suggests a landscape of perhaps 10 to the 500 possible vacuum states, each corresponding to a different universe with its own distinct physics. This could elegantly solve the puzzle of our universe's improbable fine-tuning, particularly the unnaturally small value of the cosmological constant. Why is the vacuum energy so precisely calibrated for a habitable cosmos? In a multiverse, we simply reside in one of the rare bubbles where the numbers accidentally allow for our existence. Potential evidence is sparse but provocative. The large-scale anomalies in the cosmic microwave background, like the axis of evil, could be bruises from collisions with other bubble universes in the distant past. The strange behavior of quantum particles, which seems to require multiple possibilities to exist simultaneously, might be explained by interactions across parallel worlds. Yet the core challenge remains: can we ever test an idea that, by its very nature, posits realities forever beyond our observational reach? Critics argue this moves the goalposts of science, transforming cosmology from an evidence-based pursuit into a metaphysical exercise. If every possible universe exists somewhere, does the question of why our laws are the way they are lose all its meaning? Picture an infinite ocean where each bubble universe floats with its own properties, a cosmic archipelago of realities. If this is true, what does it say about our place in existence? Are we not the center of one universe, but a mere statistical fluctuation in an infinite ensemble? This final puzzle stretches the very definition of reality, urging us to consider whether the ultimate nature of the cosmos is a single, elegant equation, or an unending, chaotic, and creative explosion of possibilities. Our journey through these cosmic puzzles is not the first of its kind. The history of astronomy is a story of profound corrections, where each answered question has ripped open a deeper and more fundamental mystery. The historian of science Owen Gingerich captured this perfectly, noting that every answered question in cosmology unveils deeper enigmas. For centuries, humanity believed Earth was the unmoving center of creation. The shift to a sun-centered system was not just a change in a diagram, it was a complete reordering of our cosmic address, one that immediately raised new questions about the scale and nature of the stars. This pattern of discovery leading to deeper inquiry is the very engine of science. Consider Olber's paradox, which simply asked why the night sky is dark. If the universe were infinite and static, every line of sight should eventually end on the surface of a star, making the entire night sky as bright as the sun. The resolution did not come from counting stars, but from a revolutionary new understanding. The universe is both finite in age and expanding, meaning the light from the most distant stars has not had time to reach us, and the energy from those we can see is diluted by the stretching of space itself. A simple question about darkness led us directly to the Big Bang. The confirmation of that primordial explosion came from another serendipitous discovery. The cosmic microwave background radiation, that faint static hiss found by Penzias and Wilson, was the predicted afterglow. It was the final piece of evidence that moved the Big Bang from a speculative theory to the cornerstone of modern cosmology. Yet this very confirmation immediately posed new riddles. Why was this background radiation so perfectly smooth, a puzzle that the theory of inflation would later attempt to solve? The same iterative process unfolded with the solar neutrino problem. For decades, detectors on Earth consistently found only a third of the neutrinos predicted by models of the Sun's nuclear furnace. Was our understanding of the Sun wrong? The answer was far more profound. The missing neutrinos were not absent, they had simply changed their identity, oscillating between different types on their journey from the solar core. This discovery revealed that neutrinos have mass, a finding that required new physics beyond the standard model, and now plays a crucial role in our theories of the early universe. Each of these historical breakthroughs, from Hubble's discovery of the expanding universe to Vera Rubin's inference of dark matter from galaxy rotations, follows the same pattern. A discrepancy appears, a mystery is solved, and in that solution we find the seeds of the next, even more challenging set of questions. The 25 puzzles we are exploring today stand directly on this legacy. They are not signs of failure, but beacons guiding us toward the next revolution. This historical perspective enriches our appreciation for every unsolved riddle, reminding us that our current uncertainty is not an end point, but the very catalyst for the discoveries that will redefine our reality tomorrow. These 25 puzzles are not isolated curiosities, but a single, interconnected web of cosmic mystery. Solving the riddle of dark energy could illuminate the ultimate fate of the cosmos, while understanding the quantum nature of a black hole might finally reveal the architecture of spacetime itself. Each breakthrough has the potential to create a cascade of understanding, where the answer to one enigma unlocks the door to the next, perhaps guiding us toward that elusive theory of everything. Carl Sagan's beautiful words remind us that we are not separate from this grand cosmic story. The calcium in our bones, the iron in our blood, every atom that defines us was forged in the heart of a long-dead star. We are the universe become conscious, looking back at itself and asking these profound questions. This quest is far more than an academic exercise. It is a journey to comprehend our own origins and our ultimate destiny. We stand at the edge of a vast ocean of knowledge with so much left to explore. Which of these cosmic puzzles captures your imagination the most? Is it the ghostly presence of dark matter, the violent brevity of fast radio bursts, or the haunting possibility of a multiverse? Let us know in the comments, as the conversation about our universe is one we build together. If this journey through the expanding universe has sparked your curiosity, consider subscribing for more deep dives into the wonders of the cosmos. Thank you for embarking on this incredible adventure, and may your own curiosity always reach for the